Welcome back to ECE 320A. We are now in Unit 8, which is our convolution unit. And to really make sense of this convolution unit, we need to start with a better understanding, or at least a connection, to the impulse response and what that represents. And that's what we are going to be working through in this video. We're in Unit 8, which means homework 8 is due at the end of this unit. We're still in Chapter 13. We're at the back side of Chapter 13, and exam number 3 will be coming after Unit number 8. What we want to do today is develop the connection between a transfer function, which we've been looking at, what we know how to do. We can find a transfer function given a circuit. We will be able to, in subsequent educational experiences, be able to associate transfer functions with many different systems. That's a very powerful concept. And now what we want to do is establish the connection between the transfer function and the impulse response. And what I've indicated here in black is how we are going to make that connection. First, we're going to remind ourselves of the input-output connection by using a block diagram. That's in the frequency domain. We should be all comfortable with that, or we want to be becoming more comfortable with that. Then we'll use the fact that the Laplace transform of the impulse function, and now what we want to make clear in this particular video and subsequent material is the distinction between the impulse function and the impulse response. Those are two different concepts. The impulse function is this waveform that exists at time t equals 0 in its generic case. It's this delta of t. It now has an infinite amplitude at time t equals 0, right at 0. And the area underneath that impulse, if we were to integrate across 0, it would have an area of 1. Even though it has an amplitude that's going unbounded, we have an area underneath that impulse function of 1, and that, together with the sifting property of the impulse, allows us to then conclude that the Laplace transform of the impulse is 1. Once we have that and this input-output connection relating the input and the output through the transfer function, we can find the impulse response is really just the system's output response when the input is an impulse function. So I'm trying to be very clear on impulse response. That's what the system does. And the impulse function, that's what we apply at the input to the system. Let's now try to make that connection between the transfer function with the impulse response. And let's begin with what we already know. We already know how to connect inputs and outputs through a system, and you can always just go back to a very basic system, but you should be very comfortable finding a transfer function, which typically we will call capital H of S, to that system. We have the Laplace transform of the input, and we have the Laplace transform of the output, and in the frequency domain, the interrelationship between the input and the output is simply this multiplication of the transfer function capital H of S with the input's Laplace transform. That produces the output's Laplace transform. That's in the frequency domain. What we want to do now is determine what's going to happen at the output of our system in the time domain when we apply at the input of our system an impulse function. Here is that impulse function, the input that we're hitting. So we're basically popping the system at time t equals 0 with an impulse, and we wait to see what happens to the output of that system. That impulse, actually, I may repeat this, I may say this, but that impulse is really energizing the system. There's energy storage devices in our system that gives rise to this transfer function, capital H of S, and this impulse, boom, it instantly then energizes all of these energy storage devices, and we then see, effectively, we will see the impulse response, but that impulse response is effectively an initial condition response because that impulse function energizes all of the energy storage devices, and then it's no longer exciting the system beyond t equals 0. What we want to do then is just remind ourselves of what the transfer function, what the Laplace transform of this impulse looks like, just so that we're all on the same page. The area, remember, underneath that impulse, if we integrate it across t equals 0 in the time domain, the area under that impulse equals 1. Here, the Laplace transform of that impulse is now, just by the definition of our Laplace transform, is going to be this integral from minus infinity to infinity of the waveform in question, which is the impulse function, delta of t, weighted by this complex exponential. And now this is sort of correlating all these complex exponentials with the waveform itself, delta of t. But now that we have that impulse underneath the integral, what actually happens? Well, that's only going to turn on, effectively, this argument of the integral at time t equals 0. Or it's now going to be doing a sift or a sifting, and we essentially then evaluate the argument or the integrand at the instant of time when that impulse occurs, which in this case is occurring right at t equals 0. Now we're looking at evaluating e to the minus s times 0. We have 0 in the exponent. E to the 0 is 1. So that is now telling us that if we Laplace transform this impulse function, we see for all values of s that the Laplace transform is equal to 1. What does the Laplace transform of this impulse equaling 1 say about the frequency content of this impulse function delta of t? And remember, if we start exciting a system with different frequencies, the system likes to naturally respond to certain frequencies. Or, I'm really saying, what frequencies are we exciting the system with? What frequencies are actually present in delta of t? And if we look at this, we can actually see that if we looked at x of s and we said, okay, what's it going to look like at a given frequency, let's say s sub 0, then that's x of s sub 0. Again, this is when capital X of s is the Laplace transform of an impulse. We've just learned that that equals 1 no matter what s sub 0 is. So it's equal to 1 for all s sub 0. So that really says, since this s sub 0 was any arbitrary, but it was a unique frequency, and this symbol really just means for all, we looked at one unique frequency, but we could look at any unique frequency, which really now says that all frequencies exist or are uniformly present in this impulse function, in x of t equaling delta of t. That's what this particular result tells us. That if we wanted to excite the system with any frequencies, then this impulse is a very good candidate to make that happen. It actually has the ability, because it has a value of 1 for all frequencies, it's now exciting every possible frequency in the system, and that's going to then tell us a lot about the behavior of our system. Now let's use that fact that the Laplace transform of the impulse function is equal to 1 to look at what happens to the output's Laplace transform. We know that that's the product of h of s with x of s. But now for capital X of s being the Laplace transform of the impulse function, that now says that that has a value of 1. This is when x of t is equal to delta of t, which is the impulse function, then y of s, capital Y of s, is actually just capital H of s. That's just the transfer function. What's that do for us then in the time domain? If we now inverse Laplace transform the output's Laplace transform, capital Y of s, that's now just the inverse Laplace transform of capital H of s, which we then call h of t. And h of t is now our impulse response. That's the response of our system when the input is an impulse function. So let me write that down. The impulse response, what I want to do now is make a few comments as to what we now are learning. The impulse response, that's how our system responds of a system which we are now labeling as little h of t. That impulse response is obtained by exciting the system at its input with the impulse function. And what, like I said before, the impulse function energizes all of the energy storage devices in our system if the input is effective at reaching those. So the impulse function energizes the energy storage devices Now all of our inductors are energized, our capacitors are charged up. That now says beyond t equals 0, what we're really seeing is an initial condition response. And if you're now familiar with or if you're comfortable with the initial condition response, now that should give you some comfort with respect to what's happening with the impulse response. It's really just going to be the modes of the system. What are the roots of the characteristic polynomial? Those are now getting excited, and we're seeing all of those in the impulse response if the input actually is able to touch or reach or connect with the energy storage devices in the system. One more comment I want to make. If, let's say, the more the impulse response, that's the output of the system due to an impulse function. So the more the impulse response, little h of t, approximates the ideal impulse function. So the more that little h of t looks like delta of t, then the more the output response, or the output waveform, will look like the input waveform. Now these statements, actually, it may take you a while to wrap your head around them, but they're very important, and I want you to kind of read over them and try to make sense of what I'm trying to explain. But now, why is that true? Well, if we looked at our connection that we know is true, we know in the frequency domain that y, capital Y of S, is equal to the product of the transfer function times the Laplace transform of our inputs, times the Laplace transform of the input waveform. Now, if little h of t is very close to delta of t, then capital H of S, we've already found what the Laplace transform of the impulse function is. That's just 1. So now this capital H of S would look almost like 1. And if H of S looks almost like 1, then Y of S is approximately 1 times X of S, or Y of t in the time domain is approximately X of t if this H of t, the impulse response, looks like or is close to the impulse function. Hopefully this will all start to come together a little bit more cleanly as we work through all of these ideas and concepts, but now we want to utilize this impulse response to examine what our systems might do to various or arbitrary input signals.